Hello, everyone. Welcome to pre-lecture 9. Today we're going to be continuing our discussion of topics in Chapter 12, specifically discussing rate laws and integrated rate laws. Okay. So last class, we had finished up by talking about rate laws equations, and so we can express these as rate being equal to some constant multiplied by the concentration of one of our reactants A to some power multiplied by, say, another reactant to a different power. Okay. And so K is our rate constant here. It is not concentration specific, but is temperature specific. And then, as I said, A and B are the concentrations of some reactants raised to some order. And so these reaction orders are usually 0, 1, or 2. And a key part of pretty much all of kinetics is that things must be determined experimentally. They can't necessarily be figured out purely from a theoretical approach. Okay. And we'd also mentioned that the overall reaction order is going to be the sum of those reaction orders. And so we're going to expand upon that a little bit today and also look at what happens once we integrate these rate laws. And so just to talk a little bit more about the units of K, basically for if we go back here and think about our rate, the rate units on our rate expression will always be equal to some concentration over some unit of time. So an example of that would be molar per second. And just a reminder, anytime you see this two exponent to the -1, that would be the same as dividing by that unit. And so this is equal to molarity per second. Okay. And so the result of this is that the units of K are determined by our overall reaction order, so that multiplying our rate constant by any of the concentrations for any of our reactants raised to the appropriate powers will be equal to our concentration over time. And so, for example, this table comes from your textbook where for a 0th order reaction, because we don't need, basically we don't have to consider the concentration of any of our species. Our units of K will just be moles per liter per second, which of course moles per liter would be another way to say molarity. For first order, so this would be, for example, rate is equal to K times the concentration of A to the first. In that case, we just have one molarity would be our unit, or any unit of concentration for kinetics there, or for the concentration there. And so we would end up multiplying the concentration times K, and it would end up being molar per second. And of course, you would just change that basically as you go, depending on the number of concentration terms that you have in your rate expression. Okay. And so moving on, this will be in chapter 12.4. I'd like to talk about integrated rate laws. And so thus far, the rate laws that we have discussed relate to the concentrations of reactants and the rate of a reaction. Okay. And so if we take those rate laws and we perform an integration on them, if we were performing calculus, then we can get a different form of these rate laws that would be called integrated rate laws. And these can be used to determine the amount of reactant or product present after a period of time, or to estimate the time required for a reaction to proceed to a certain extent. And so this can be very useful information if we're thinking about the rates of reactions or how long a reaction might take. And so, as the name would imply, especially the integrated part, these rate laws are ultimately derived from calculus. We won't be going through the derivation in this class, but if you continue on into upper division chemistry, you would, of course, go through the derivation of those. And our goal in this chapter is to understand essentially how they relate the concentration of a reactant and how much time has passed. Okay. And so the first one that we'll talk about are called first order rate laws. And so this would be the equation that you get when you integrate an expression that says our rate is equal to some constant K times our concentration of some reactant A here. And so we end up with this equation where the concentration of A at any time is equal to our initial concentration, A naught, times the mathematical constant e raised to the power of negative k times t. And so k there is our same rate constant as our initial rate expression, and t represents time. Okay? And if you were to rearrange this equation just a little bit, essentially take the natural log of each side, then you would be able to get essentially a y equals mx plus b form of the equation here, where our concentration will decrease over time. And if a reaction is a first order reaction, then our y-axis, if we have the natural log of our concentration of whatever species, in this graph it is hydrogen peroxide, versus time, then we would see a straight line, again, if our reaction follows first order kinetics. Okay? We can go ahead and contrast that with what our equation would look like for a second order rate law. And so again, if we were thinking about rate here, this would be where our rate is equal to k times a squared. And so this would be, if we performed an integration on this, we would end up with an equation where 1 over our concentration at any time, as shown here, is equal to kT plus 1 over our initial concentration of A. Okay. And so if we were to plot data from an experiment, say we collected data points, and on one axis, for example, this y-axis, we took the natural log of something, and then we contrasted that with 1 over the concentration that we measure, then only one of these should give us a straight line. And so you can see from this diagram here that we have a curved line when we try to fit this using first order integrated rate law. But when we use our second order integrated rate law, we end up with a straight line. And so this tells us that, yes, this reaction must follow a second order kinetics. Okay. We also have zero order rate laws that can exist. And so at this point, this is where the concentration or the rate of reaction is essentially going to be independent of the concentration, or at least we won't have to modify it. And so this is the rate law expression that you would get, essentially where we don't have to modify anything with natural logarithms or fractions. And so our concentration at any time is going to be equal to negative kT plus our initial concentration, which is again just a y equals mx plus b kind of format. Okay. And so if we were to plot the data for zero order kinetic experiments, then we should be able to come up with a plot like this, where again, when we have a straight line, we know that when we plot, again, just our unmodified data here, you'll notice this is just the concentration of ammonia, NH3 here, versus time. When we get a straight line, we know that this decomposition over W here, which is the element tungsten, would be zeroth order, whereas if we're looking at decomposition on SiO2, silicate right there, that would be a definitely not zero order. It would probably be a first order kinetics. Okay. And so those are the three kind of integrated rate laws that we'll talk about. And again, we typically will need to identify these experimentally by plotting the data. And so that's generally the easiest way to tell. To finish up the pre-lecture, I'd also like to talk about a half-life of a reaction. And so this is can also be referred to as T1 half. And so this can be a little tricky to conceptualize, and it is defined as the time required for 1/2 of the given amount of reactant to be consumed. And so you'll notice that we report it as a time, but what we are actually measuring is when 1/2 of a given amount of reactant is consumed. Okay. And so for each succeeding half-life, half of the remaining concentration will be consumed. And so once we get to one half-life, we would have one half left. Once we get to two half-lives, our half would be halved again, and so on. Okay. And so, due to different rates of reactions and different kinds of rate laws that we just went over, each type of reaction and rate law will have a different equation that we would use to calculate the half life of a certain reaction. And so, for first order rate laws, the half life would be equal to the 0.693 divided by our rate constant k. Something that's unique for our first order half-life equation here is you'll notice that it does not depend at all on the initial concentration of whatever we are measuring. And so this is particularly useful for something like carbon dating. Actually follows a first order decay of a radioactive carbon species. And that's how we're able to tell how old things are by carbon dating, because we don't need to know the original concentration of this carbon isotope. We just basically have to solve for time. Okay. If we took the equation for the second order half-life, this is what it would look like, where again, we now have the appearance of the term A sub naught. And so in the case of a second order decay of, or yeah, I guess, decay of reactant or half-life measurement, it will depend on the concentration of our initial amount of whatever we're measuring, and then 1 over the rate constant there. Then finally, for zeroth order, the half-life can be measured by taking the initial concentration, which again appears, dividing by 2 times the rate constant, k. Okay. All right, and so pretty much all of the useful information we've gone over, both in this lecture and at least part of last lecture, is found in table 12.2 here from your textbook. I would recommend, I don't know if memorizing is absolutely necessary, but you should definitely be familiar with this table. And I can assure you that if you are familiar with it, it will make your life a lot easier heading forward. Okay. That concludes the pre-lecture video. I hope that you found it useful. And if you have any questions, of course, feel free to let me know via email or in class when we start up on Tuesday. Right, take care, everyone. Bye.